Okay, let's just jump right in here. This is usually one of my favorite lessons to teach when I'm presenting to a live audience. We'll see what it's like when I'm presenting to a bunch of chairs and desks. Anyway, in the last lesson, we looked at producing sound, producing not just sound, but music, I guess, pleasing sound, using strings, and talked about how we could determine which frequency that we would get on the string if we knew the speed of the wave in the string and the length of the string. We talked about different things that would affect the frequency of that string. We're also going to look today at air columns, and we're just going to limit our discussion of music and musical instruments to those two types of instruments, string instruments, and ones involving air columns like brass instruments. So what do we mean by an air column? Well, it's a length of tubing. It doesn't necessarily have to be all one long tube. It could be curved around. It could be in the shape of a bottle. It could be in the shape of a brass instrument. It could be a long tube as well. In any event, there's a couple of different versions that we're going to look at. One of them is when it's open at both ends, which is called an open air column. And if it's closed at one end, it's considered a closed air column. Now, a closed air column is not closed at both ends. If it's closed at both ends, then there's really no sound that's escaping. If it's closed at both ends, we call it a string. So, open air columns and closed air columns. So if we produce some sort of source of vibration at one of the open airs of the column, you'll notice that we only hear some frequencies. And I can take a pop bottle and I can blow across the top, and you hear that frequency. There's only one frequency that you're hearing, plus all of the harmonics, just the same way as it was with strings. But that's not the only frequency. It's my vibrating lips that are producing the sound. But when I vibrate my lips like this, I don't get any specific sound. There's a whole bunch of different frequencies, and none of them are any louder than the others. So why is it that when I do that same type of thing over a pop bottle or into a tube, that I get a certain frequency? Only some frequencies are produced because they have to have the right wavelength. And what do we mean by the right wavelength? Well, it's the right wavelength to produce, not surprisingly, because we've talked about it several times now, to produce a standing wave. Standing waves are the main culprit, I suppose you could say, in mechanical resonance. When every object has its own frequency which can be vibrated, that will produce a standing wave inside the object. And so that's how a mechanical resonance is achieved. Essentially, what we're doing is we're creating mechanical resonance in a string in the last lesson or in an air column in this lesson. When we have a standing wave, the effect of that is that it increases the amplitude of the wave. And if the amplitude increases, it makes the sound louder. So only certain frequencies will be louder. So when I vibrate my lips in the air column, and I'll show you a picture of that air column a little bit later, when I vibrate the lips in an open air column, there's only one frequency or a set of specific frequencies that will create the standing wave, so it's only those frequencies that you hear. There are other frequencies that my lips are vibrating at, and there's other frequencies inside that too, but it's not creating a standing wave, and therefore it's not amplified, and you don't hear it. So let's jump into looking at, first of all, an open air column. So there's a picture of the tube that I was just blowing into. I've got two tubes, just a meter stick there just for scale. This is the exact tubes that I'm using, and I can slide all I've done with these red parts over here right there and right there. That's just a piece of bristle board that I've rolled up so that I can kind of use it to slide in and out. So I can go. And so as I slide the tubes in and out, I get different frequencies, and we're going to see why that's true. If you're looking at that and thinking, or listening, I suppose, and thinking, well, it's like a trombone. That's exactly what it is. The trombone does exactly the same thing, except the length of tube is a little bit different. Obviously, it's going to create a much nicer sound. This is a little piece of plexiglass tubing with cardboard on it. I would imagine trombone is a little bit more expensive. So one of the things that you'll notice here is that it is open at both ends. So open here, it's open here, which is why we call it open air column. But when we're looking at the wave, if we're producing a standing wave in here, it's going to be a little bit different than the standing waves that we looked at when we have a string, because we need vibration. When I put my lips onto the open end over here and I blow into it, I'm not really just blowing into it, I'm creating a vibration. The air there has to be able to vibrate a lot. And so what you're getting, and you're producing a standing wave, is you're actually getting an antinode at this point. And you're going to get an antinode at the other point as well. So if I just draw a picture of what this air column would look like, I'm going to use a black air column here. Something like that. Here's my air column, just kind of a cross-section of it. And the wave that's being produced is going to have, it's a standing wave. Actually, before I draw that, let's just draw a kind of a typical a general standing wave, the way we would have drawn it before. So it looks something like this. So what we need are standing waves at each end. Antinodes at each end. So here's an antinode, and the simplest place, and here's another antinode, and so that section of wave is part of a standing wave. That is your standing wave, despite the fact that it doesn't have a fixed end on each end like all the other standing waves. So when I draw a diagram of that, it's going to have kind of half a wave over here like this, and half a wave over there like that, and that's the simplest standing wave that I can get. That is an antinode at each end. Why does it need to be an antinode at each end? But remember what these waves symbolize. They symbolize how far from the equilibrium point a particle is at a moment in time. And so in order to hear sound, the particle has to vibrate from being on one side of the equilibrium going back to the other side of its equilibrium point. Think back to chapter 7 when we looked at how sound was created. So the particles will vibrate back and forth. At this point, right over here, I'm going to mark in with a green arrow, at that point right there, those particles, since that's a node, and we know from a standing wave that in a node, the particles don't move. And so at that point, the particles never move from their equilibrium position. You get no sound whatsoever at that point. Over here, when the particles are vibrating at the end, they're vibrating back and forth. Not only are they vibrating back and forth, but they're amplified. Remember, the standing waves amplify the wave. So the particles are vibrating back and forth a lot, and that's what produces a very loud sound. So if you want to hear the sound coming from our air column, you need to make sure that there is an antinode at the end of that air column. There will also be an antinode at the other end of the air column, because that's where the sound is being produced from in the first place. So that's the frequency that will produce that right wavelength. And remember that here's the length of your tube, just the same way that we did in the air columns. I think I was using a capital L, so let's try to be consistent here. There's the length of your tube. And you'll notice that if we trace that section, that's only half a wavelength. So that length is half a wavelength. So it kind of looks a lot like the strings, except with a string, it goes from node, say right over here, we'll say, to the next node. That's your simplest standing wave. In an open air column, it goes from antinode to antinode. But otherwise, the derivation would be exactly the same. V equals F times lambda. So the fundamental frequency, F1, is equal to the speed of the wave, which is the speed of sound in air at that temperature, divided by lambda. We can see from here that lambda is equal to 2L, so we get the same type of formula that we had with strings, where the frequency is V over 2L. Because of that, we're going to get the same patterns as we got before with strings. So the next simplest, inside that particular length of tubing, the next simplest standing wave would look something like this. So there would be 2 notes in there. And here's your length. That's also 1 wavelength. If we start from the top over here, and we move down there, there's half a wavelength, that's your full wavelength. So lambda L equals L, and similarly F2, the second harmonic, is equal to V divided by lambda, which means V divided by L, which is exactly twice what F1 is. And you could draw other diagrams that would look a lot similar to this. So something like that. There's your third standing wave. So you have, here's 1 wavelength there, and then another half wavelength. So L equals 3 halves lambda, or lambda equals 2/3 of an L, and we would end up with F3 is equal to 3 times F1. And so we get the same pattern as we did with strings. And so it's in the same way that we have with strings, what you're going to hear is very, very likely that fundamental frequency. So notice that the larger L is, as L goes up, then the frequency will end up going down. The frequency is inversely proportional to L. So as you can probably imagine, on my makeshift trombone, that was me taking the cardboard or the Bristol board and moving it in. And the frequency went up as the length went down. The frequency would go down as the length goes up. So here I'm going to extend it. Now, you probably noticed if I keep one length, let me just pick a length that's easy to produce a nice sound. Now, anyone who's played a brass instrument, I used to play one in high school, knows that that you can produce more than one sound through the same length of tubing. There's really only 8 combinations in most brass instruments, like a tuba or a baritone or a trumpet. There's 3 keys. It can be held in 8 different combinations. And so you only get 8 different lengths of tubing, but you can hear the harmonics of the fundamental frequency. So it's a little bit more difficult to do this. Please bear with me. This could sound really bad. So you can get this sound, or if you try a little bit harder. So both of those sounds are heard. One of them would be the second one is a higher frequency. So what you're actually hearing is a harmonic of that original fundamental frequency. So what does this look like in closed air columns? Well, closed air columns are a little bit different. These ones you're probably familiar with. There's some pictures of some bottles that I have here just for this occasion. And you'll see, and I tried to put a little bit of dye in the some coloring in the bottles on the right. So the first bottle is just a regular pop bottle. The other 3 are glass bottles. The first one is empty. The second one has a little bit of water in the bottom, and the third one is about half full. So when I blow across the top bottle, you're going to see we got a very low sound. When I use the slightly shorter empty glass bottle right next to it. So to compare, when I use the bottle that is a little bit filled, and when I use the bottle that's more filled, so the similar to the open air column, as the length goes down, the frequency goes up. What's happening here is that at the closed end, so basically what we have at the very, very top, we have an open end. And at the bottom here, the sound can't vibrate because it's basically hitting the wall. The glass isn't going to vibrate, so the air right next to it is going to have a hard time vibrating as well. So this is a fixed end, which creates a note at that end. So that's what makes this different from the other air columns, that here you're going to have a node. At the top it's open, so you're going to have an antinode. So you get an antinode at the open end and a node at the fixed end. So let's see what this looks like. I'm going to draw these vertical rather than horizontal. It really doesn't matter. So there's my column. That's my closed air column. You see it's open at the top and closed at the bottom. So again, let me just draw the standing wave. So there's my standing wave. So the way this is going to work is you have to start with a fixed end. So let's start right from the very, very beginning. There's your fixed end. And the fundamental frequency is going to occur at the first open end, which is only right over here. So what that diagram will look like is open at the top and closed at the bottom. So here you get, there you get your node, which means that there's no sound right there. But you will get a lot of sound. You're still going to get a loud sound up at the top. At least when the frequency is right for that particular length of tube in order to be able to hear it. So the derivation looks pretty much the same as last one, except you're going to notice that the pattern is going to be a little bit different. So here's the length of your tube, and you may notice that you're not getting, let me get rid of this, that's not really needed anymore. You're not getting a half wavelength anymore. So this whole thing, let me draw this in red, starting from here on our standing wave, that's a full wavelength. Half a wavelength would put you right over here. So what you're actually getting here is 1/4 of, I say 1/4 and then I write 1/2. 1/4 of the wavelength. So 1/4 of a wavelength equals L, so lambda equals 4L. So the wavelength that's going to produce your fundamental frequency is 4 times the length that you have in that particular tube. Once again, F is equal to V over lambda from the wave equation, so our fundamental frequency is V over lambda, which is equal to V over 4L. So notice that this is a little bit different from the V over 2L that we had been getting before. So let's look at, so there's our fundamental. There's our fundamental frequency. And so let's look at the first harmonic. So we still have the same length of tubing, except now we need to go to, now we're still going to have our node at the start, and we need to get to the next antinode, which is right over there. So drawing these diagrams, it's going to look like this, and go right to a node in that spot. So we've got 2 nodes now, one right over here and one down at the bottom. We've got 2 antinodes as well. The only node that we're worried about is the one at the bottom. The only antinode that we're worried about is the one at the top. You should be able to figure out how many wavelengths are in there. Take a second, pause it if you need to, try to figure out how many wavelengths, and then start over again and see if you were right. So this gives you 3/4 of a wavelength. So again, 3/4 of lambda is equal to L, so lambda equals 4/3 of L. So the second harmonic is V over lambda, which is V over 4/3 of L, which is 3 times V over 4L, or 3 times the original frequency. So our second harmonic is 3 times the original frequency, not 2 times the original frequency. So our pattern doesn't work anymore. Well, let's see what kind of pattern we do get. Let's look at the third harmonic. So the third harmonic is going to give you, so I'm going to start here, we're going to get a node, there's our antinode, another node, there's our antinode, and there's our next node. So that's what our standing wave will look like over here. And if we say, okay, there's our length, the length hasn't changed, and we're going to start off over here. I'm going to try to figure out how many wavelengths this is. Start off over here, go down this half a wavelength, up to a full wavelength, and then I go another quarter. So 1 1/4 wavelengths, or we can call that 5/4 of a wavelength, which means that, skip some steps here, L is equal to 4/5, or sorry, L is equal to 5/4 of lambda. That's why you don't skip steps. 5/4 lambda. So lambda is equal to 4/5 of L. So the third harmonic is speed over the wavelength. That speed, remember, is the speed of sound inside the air column, divided by 4/5 of L, which means 5 times V over 4L, or 5 times the fundamental frequency. So you may see a pattern developing now. I don't want you to memorize this pattern. What I'd like you to do is look at the process in order to get there. So if I say, what is the fourth harmonic, you don't have to go through the fundamental, the first harmonic, the second harmonic, the third harmonic. You can just go, well, the fundamental is the first harmonic, but you can just go directly to drawing the diagram. So you should be able to jump in without having done the first two diagrams. You should be able to jump into this. What I would strongly suggest is drawing the standing wave that you see over here, drawing that standing wave and using that as your basis for both strings and air columns, open and closed air columns. That can be your basis for starting to determine the lengths of the wavelengths that you need and what that frequency is. So let's look at a couple of examples here. Oh, and by the way, just before we move on, if you look at this formula, again, you get that the length is inversely proportional to the frequency. So the longer the length, the lower the frequency is going to be. Now, there is a little bit more to it than just the vibration of the air columns, and it's one of the reasons why doing this on a glass bottle and a plastic bottle may sound a bit different. So don't, try to, you can't really design your own, at this point, you're not going to design your own musical instruments based solely on these types of calculations if you're planning on putting together a band using only pop bottles. There's a little bit more to it because of the vibration of the glass and the vibration of the plastic. But this will give you at least a good impression of how the length will affect the frequency. Let's look at a couple of examples here. In the first example, we have a 75 centimeter long tube that's open at both ends, and we use it as a noisemaker in a sporting event. You've probably seen these types of things. They just look like big horns. They're kind of fluted out at the end, and that just, when I say fluted out at the end, it looks kind of like this. And that part at the end is just to make the sound louder. Okay, it spreads out the sound a little bit more, so there's more area of air that is being compressed and rarefacted. So we don't need to worry about it. Doesn't that fluted part at the end doesn't really make a difference for our calculations, only for the excuse me, only for the volume. So if the air inside the tube is at 28 degrees Celsius, what's the fundamental frequency, the third harmonic, and the fifth overtone for this instrument? What I'd like to do actually is let's start backwards. Let's start off with the fifth overtone. So I said before, draw yourself a standing wave. And what we're looking for is an open tube. So there's my open tube. My standing wave for an open tube is going to start at an antinode. So my fundamental would be right here, first harmonic, second harmonic, third harmonic. Well, the fifth overtone is actually your sixth harmonic. So think of one as the tone, first overtone, there's your tone. This is your first overtone, second overtone, third overtone, fourth overtone or fifth harmonic, fifth overtone or sixth harmonic. So that's what your wave is going to look like. So we're going to get so 1 crest, 2, 3, 4, 5, 6. See if I have that right. 1, nope, I need one more. So again, this would be where the first harmonic, or the first harmonic would be second, third, fourth, fifth, sixth harmonic. So the fifth overtone, that's your sixth harmonic. So I don't want you to just jump straight into, well, let's figure out the fundamental frequency and multiply it by 6. Draw the diagram. That's only half of your standing wave. Here's the other half for completeness sake. There we go. Here's the length of your tube. That's L. How many wavelengths do we have here? Well, we're going to start off over here at the beginning, and there's one wavelength. There's 2 wavelengths. There's 3 wavelengths. So L is equal to 3 lambda, or lambda is equal to L over 3. Well, we know that L is equal to 75 centimeters, or 0.75 meters. Divide that by 3, and it gives you a wavelength of only 25 centimeters, or 0.25 meters. We need to figure out what the speed of sound in that 28 degrees Celsius air, 332 plus 0.59 times 28. Use 28 degrees Celsius because as you would blow through this instrument, the air inside the instrument would heat up. Again, those of you who've played in a band, who've played a brass instrument, and probably other types of instrument know that you have to warm up your instrument. And this is one of the reasons why. First of all, the instrument itself will expand when it's heated up. But secondly, the air inside it will change temperature, which means the speed of the wave changes. And if the speed of the wave changes, then the frequency that's going to be played is going to change as well. So you have to warm up your instrument and try to keep it at the same temperature. I can imagine that this would be something difficult for, say, marching bands marching in the Oktoberfest parade, and it's cold outside. You'd have to find a way to make sure that your instruments stay relatively warm. So when we do that calculation, 0.59 times 28 plus 332, it gives you 348.52. So the frequency that you get is the speed divided by the wavelength, which is 348.52 divided by 0.25, which is the same thing as multiplying by 4, and that gives you a frequency of about 1,394 hertz. So in this particular instrument, that fifth overtone would be 1,394 hertz. So going back, actually, I think I'm going to skip, just in the interest of saving a little bit of time, I'm going to skip the third harmonic, because really, if you can do the sixth harmonic, you can do the third harmonic. If I would ask this on a test, one of the reasons I would do this is just to see whether you understood that the fifth overtone is the sixth harmonic. The fundamental frequency, on the other hand, is probably worth doing. You may guess that it should be a sixth of that, and we'll see if sixth of 1394. We'll see if we actually get that. So here's our tube. Here's our wavelength for our fundamental frequency. L is equal to half a wavelength. So lambda is equal to 2L, which is 1.5 meters. So that's a much larger wavelength, which means it's going to be a smaller frequency. The frequency is V over lambda, which is 348.52 divided by 1.5. As we can see, this is going to be quite a bit smaller. 348.52 divided by 1.5 gives you 232 hertz. So that would be a fairly low sound. And you would hear that sound, and you would probably hear quite a bit of the harmonics as well, because at 232 it would be fairly difficult to hear. So 464 would be a little bit easier. You'd probably hear that sound as well, and possibly many more of the harmonics. The second example that I wanted to do concerns a closed air column. So in the lab on Friday, we're going to do something very, very similar to this. So we have a long tube that's partially filled with water. You may have noticed these long tubes sitting at the back of the class. They've been there all year. They have little tubes connected to a reservoir of water, and we can use that reservoir of water to adjust the height of the water inside the tube. So you have a great big long tube like this, and the water down here, probably should have used blue for water, but our water is going to be black. That water can be adjusted. So what we're looking for is trying to figure out what water level is going to produce standing wave and giving feedback to amplify the sound. Now, you can create a standing wave without getting feedback. And that would give you, basically, the sound would disappear, and you wouldn't get any resonance in that length as well. What we're going to look for is the place where we do get a loud sound. So in that case, we have, so the simplest one is going to give us a node at the bottom and antinodes at an antinode at the top. So our wave would look something like this. It's a very stretched out wave, but again, the length of the tube is going to be equal to a quarter. The second time I've done that, where I've written half when I've said a quarter. The length is a quarter of the wavelength, so 4L equals lambda. In this case, I'm trying to figure out what lambda that I actually need. Let's use, just for simplicity, let's use the 28 centimeters, 28 degrees Celsius, I should say, that we used in the last question, which gave a speed of 348.5 something or other, 348.52 meters per second, notwithstanding our significant digit issues here. So if I know that the frequency that I want to hear is 1,000 hertz, and the speed of the wave is equal to 348.52 meters per second, then rearranging the wave equation, I get lambda is equal to V over F, which is 1,000 divided by 348.52. I get a wavelength of about 2.87 meters. 2.87 meters, the fairly large wavelength. So the length of the tube has to be 1/4 of that. So L is 1/4 of 2.87 meters. and that gives you approximately 71.7 centimeters. So when our tube was at 71 point, if the water drains down to a level that is 71.7 centimeters from the top of the tube, you would hear this kind of feedback sound. And you're going to be able to hear that fairly pronounced when you do the lab on Friday. And you would get a really loud sound, and that tells you that you're getting a standing wave or resonance inside that tube. There would be other lengths that will do that as well for this particular frequency, because it's not just L is equal to 1/4 that will give a standing wave. We could have something that looks like this. Now, in this case, what we're doing, instead of keeping the tube length the same and saying that we're getting different frequencies that you're going to hear, in this case, you're going to hear the same frequency, but we're going to change the length of the tube so that this is what we had. There's my 71.7 centimeters, and this will keep going, and I'll readjust my diagram a little bit here. At this point, so this is at 71.7 centimeters. When the tube is, when the water's down to here, it will also produce a loud sound where you have your node down at the bottom, and you get an antinode over here, but you also get an antinode over there. At what length would that happen? Well, we can probably see that from there down to here, that this is 3/4 of a wavelength. Well, we already figured out what the wavelength is, 2.87 centimeters. So that length, in this case, the length is 3/4 of 2.87. So 3/4 of 2.87 gives you 2.15 meters. So if we had a long enough tube, we would be able to, as we were bringing the water down, you would hear a really loud sound. You would just hear the regular 1,000 hertz coming out of the of whatever device is playing the 1,000 hertz sound. As you brought the level down to 71.7 centimeters, level the water down to 71.7 centimeters, you would hear a loud feedback from inside the tube. That's mechanical resonance. When you went a little bit lower, you would be able to hear mechanical resonance again when the tube length is 2.15 meters. When it's 3/4 of a wavelength, you would hear the same thing at 5/4 of a wavelength, at 7/4 of a wavelength, and so on. That's always going to give you resonance, constructive interference, if you will. What would happen? Is there any way that we can get no feedback at all from this tube? What we would need to do there, we notice that you have to have a node at the bottom. So you have to have a node over here. And when we get a loud sound, we have an antinode at the top. So if we want a quiet sound, all we have to do is position the length so that you have a node at the top. So when we can adjust, if we, in this case, we're keeping the frequency up that the air is being vibrated at the top. We're keeping that frequency the same. So this is a little bit different than blowing into a tuba or a trombone, because there you're getting a whole bunch of frequencies and you're going to hear the loud one. In this case, we're using one frequency. Maybe we put a tuning fork at the top here, and so at a particular length, you're only going to get one frequency. So the wavelength is set at a particular length of water. You get a node at the bottom. You would also get a node at the top. When we get an antinode at the top, we hear the sound loud. When we get a node at the top, we hear the sound very quietly. So where would you hear the sound quietly? Well, notice that this is half a wavelength. So L would be equal to half lambda. So lambda is equal to 2L. Or we already know what lambda is. So the length would be 1/2 of the 2.87 meters, or approximately 1.43 meters. So at 1.43 meters, the sound coming from inside the tube would essentially disappear. That would be destructive interference. Okay, so that should give you lots to go by. There's lots of really good questions in the textbook in this section, so make sure that you go through it and you do them. As I mentioned before, I expect you to be essentially done Chapter 8, or at least done most of Chapter 8 by the time we get to the lab on Friday. The more you know from the chapter, the easier the lab is going to go, and we should be able to get through everybody's groups all on Friday, and then we can just review what we need to on Monday, and then have or not Monday, Tuesday, because Monday's a holiday, and then we can be ready to go for Wednesday.